So, my name is Evgenii, and we'll be talking about your sanity, my sanity, and how to use sanitizers. So, my name is Evgenii, the second name is unpronounceable. I work in Bloomberg, and I got PhD in some kind of academical computing with GPUs, LLMs, not LLMs, LLVM, not LLM. It's a major distinction. And I write mostly C++ and Rust, and I'm truly passionate about safety with memory, with languages, with systems. So we'll be talking about this. So first of all the opinions are not from Bloomberg, from my own. So I don't express any views of my employer, but I'll definitely talk a bit about how do we do this in Bloomberg. So the outline, we'll touch about sanitizers for approaches we can use to ensure memory safety, how to build stuff, how to actually sanitize your code and find bugs, and we'll go to case studies for a different set of examples and how to use them. So, stay sane, please. First of all, which approaches do we have to ensure safety? Of course, static analysis. We have a lot of tools. They don't require any changes in source code, in binaries, all good. Then we can emulate and run it somewhere. And also no code changes, no binary changes, that's good. Then we can go with instrumentation. So it requires only binary changes, no source code changes, star. And we can also rewrite our code and get rid of any erroneous behavior. So for static analysis, there are plenty of tools, Tidy, CodeQL, commercial tools, a lot of them. They can probably tell you about problems, but the heuristics are quite limited. Then we can go with simulation. For this, the most popular instrument is probably Valgrind, Hellgrind. Instrumentation is the topic of our talk. It's about LLVM. There are also commercial tools from IBM, Dimmalog, whatever. And yeah, as usual, we can write without errors. So we are here. Sanitizers, what are them? Actually, you know probably about 4 of them, major sanitizer tools. RG sanitizer, memory sanitizer, undefined sanitizer, and chat sanitizer. There is another one in the middle, hardware sanitizer. I'll speak about it later. Since I'm unable to find any additional bottles of sanitizer in my office, we'll not speak about extra sanitizer tools, and actually they're not so useful, probably, so we'll only focus on major tools. So how to build them, how to package them, and actually which flags to pass to our favorite build system. So when it's a simple application with our favorite build system, it's only a matter of one flag. Yeah? We just pass sanitize address, and that's all. The whole program is instrumented, linker is OK. So is this all? No, unfortunately it isn't. If our program became a bit more complex, so we have an application, we have a set of libraries, static, dynamic, whatever. We need to pass instrumentation flags to all of compilation units, to all libraries, and also instruct the linker on the left side to use Sanitize to actually link runtime into the program. Quite a bit. It requires source code changes. So the ways to enable it in CMake, we'll speak only about CMake here, not Bazel, not all the stuff. It's really, really flexible. Unfortunately, it's too flexible. So we have plenty of options how to enable it. First of all, we can just pour some target compile options to the code. It's OK. We can also specify it from external call, CXX flags, quite fragile, but could work. Then we can make a special option just to enable sanitizer or not, just a normal CMake option. And finally, we can go with a special CMake build type. All of them, unfortunately, require some changes to your build system. So it's not probably a good approach. Yeah? Then, if we go with a really modern C++, we have toolchains. So the toolchain file on the right side, it's just a set of different CMake instructions, and it could be passed from outside. It's fully supported by EDA, IDEA, CI, and it's really standard way to go. Yeah? So we don't need to adjust anything at all in our system. When we move to from one project only to a set of projects, we can go with choice of package managers. So we'll speak about Conan. It's open source, JFrog Conan. package manager. It works with all the instrumentations via profiles, usually. So profile is just a set of instructions about how to build software, where to find flags, where to find linker, what to provide. So it means when we can provide instructions to Conan how to build our package and all the dependencies via packages. And it requires all the packages to be rebuilt because the flags are not part of our package. It's a part of host system. So unfortunately, we need to rebuild all of them. Lucky us, from Conan 2.0, which is probably 5 years old now, we support symmetrical chains natively. So we use the same profile. We don't tweak it. Unfortunately, the chain is after-generated for each build. So it's not permanent, it's transient. We need to put something outside build directory, apparently. So the recommended way of extending CMA here is just to use user toolchain. So on the left, we point system to use user toolchain, and it could be stored somewhere outside the package. And here we specify all these compile options, leak libraries, flags, and all of them. So this is the way to go with Conan. If you don't use Conan in your package manager package system, it could be another approach, but the main idea is this. So actually, what to provide, which flags to provide. We don't want to optimize call frames, so it's not about performance, it's about correctness. It means if we avoid the distinction between different functions, we'll get unreadable stack traces. So don't do this, use debug info, and pass fcommon. Then we don't want to change behavior because we'd like to test the same program with exactly the same behavior. It means we don't want to turn off optimization. Please pass O1. And since we don't want to slow down it more than sanitizers allow us, we need to specify at least O1. So with modern practices, we actually don't require any source code changes. We don't require build flag changes in CMake files, whatever. And system manifest also stays the same. So actually, it's pretty good. Really impressive. So let's speak about sanitizers themselves. So what's inside? How do they work? And let's dive deep into them. Specifically about address, memory, and thread. And click. So Edge Sanitizer, it's most used and most useful one from all of them because it allows us to overcome the main problem with C++, the memory safety. It's supported in both CLang and GCC. Sorry, I cannot speak about MSVC. No idea. It catches different class of errors, and most useful for us are out of bounds. Use after free. So when we just go to the same memory after free, double free, and use after return. So actually, it covers all the typical CVEs which we can find in our programs. So how does it work? 2 stages. The first stage is to instrument. We need to replace all the memory accesses from our program, whether it's read or write, with special calls to the library. So it looks pretty slow, but it works well. Then, on each memory access, we need to check if a specific piece of memory is accessible or not. If it's OK, we just pass. If it does not, we report. Yeah. And for stack memory, not heap memory, we need to guard it with special buffers. I'll speak about it later. So it's about how to instrument. It's during compile time. And during load time, when we launch our program on the host system, we need to intercept all all calls from libc with our own calls to allocate memory, free memory, go to, I don't know, with thread sanitizers to pit thread logs and all the stuff. And also we need to provide diagnostics when a program actually crashes, right? So 2 different steps. Let's finally crash something. So I really hope you see the bug here. It's just out of bounds error in heap, right? So usually you just break, right? So if you check the trace here in really, really fine. Do I have a pointer here? Oh yeah, I do. Let me add a pointer. So we're trying to access this memory, which is definitely heap because it's a high address. You can tell it by the first number of address. And what do we have? We have the exact line of program where do we crash, right? And then we got, it's about heap. OK, fine, it's not about stack at least. And then we got exact memory address when we try to access a specific byte. So if you do all these calculations, we can easily decide that, OK, it's index 6 in 32 bytes array. So seems like we're trying to access the 6th byte. Fine. This example from Slang, so you can probably get another results on different platforms, but the main idea is you get all the information. Then, how does it work? Actually, if you can see, this memory we saw in the previous slide, 1602, whatever, it does not match to this memory snippet in this slide. Yeah, it's different. So the faulty memory is definitely not 1C04, right? What is it? It's shadow memory, so the answer lies in shadows. The shadow memory is a special region which is allocated when your program starts. So it's done by runtime, in load time of your program. On Macs, it's located in these addresses, on Linux, in these addresses, and I suppose it was run on Mac, yeah? So it means the shadow memory is allocated there. So all these addresses from the real memory, they are tracked in shadow memory by a really simple formula. Actually, we can see all this memory, like the representation of memory. White bytes are addressable, and colored bytes are poisoned. So if we just hit any poisoned byte in shadow memory, we will trigger a report. That's it. So if you go in a really naive way, we'll twice memory usage. We'll have twice memory because for every byte, we just go and do the same. So what do we do to optimize it? First of all, each 8-byte segment is coded in only 1 byte in shadows. So if we allocate all the heap memory aligned to 8 bytes, it works fine, right? So when we try to access the memory in main memory, we just go to special function, which is inserted by instrumentation. So instead of just reading a byte, we go and check, OK, report load 4 because it's 4 bytes, right? And on this picture, you can see on the left side, it's main memory. On the right part, it's shadow memory. So let's try to read and resolve shadow address. So if shadow isn't poisoned, so we're trying to read the 4th byte, and the row is 3, right? So poisoned bytes are red, green is good, yeah? So shadow memory tells, OK, 6. What does it mean 6? It means in this memory chunk, 6 bytes are addressable. OK, so we just try to understand, is our byte below 6 or after? If it's below, it's OK. We can just read, pass. If shadow is fully poisoned, it's the last line. We just report immediately because any access to this area is poisoned. But if you're just in the middle, for scenario 3, the shadow is partially poisoned, and it's the line with scenario 1, 3. We're trying to read the 4th byte, but in shadow it says, OK, only 2 bytes are available. We just raise immediately. So that's the idea how Sanitizers work. Really simple idea, but it took 10 years to master it and to make it really accessible to your program and for developers to use it. So actually, if you remember, we have 2 kinds of memory. So one type grows from top, another from bottom. So app memory starts around, when we sanitize the program, around 140 gigs. And then we got a really, really huge gap until we have stack. So the shadow memory is reserved. I'll speak about it later. If we're trying to catch any errors in stack, how can we do it? Because we don't allocate this. It just lies somewhere in stack. So what Sanitizer does is it uses another approach. And I'll speak how it looks like later. So first of all, let's crash stack. It will be Stack Overflow now. We go to the 6th byte in this array. So in naive approach, it should be the byte which corresponds to test interpreted as int, right? Because it's just one byte after the param array. OK, so we have 20 bytes for param, and we have 13 bytes for string. They are located on stack, so it means when we try to access it in instrumented program, we'll see, OK, first of all, it's stack buffer overflow. Fine, we got the problem. It's addressed in 16th line of program. Trust me, it's this. And then it prints, OK, we got 2 frame objects. So it's not one giant stack. It tells us explicitly that we have access in this specific memory region, so it's fine. We got all the information required to understand even addresses and offsets where we have a problem. So each protected area is surrounded with some kind of zones which are protecting them from accessing, and all the red zones around them are actually mapped to the shadow memory. So we have exactly the same behavior. And of course, it should be aligned to 32 bytes. So how does it look like? Here we got 20 bytes. Here we got 13 bytes. All of them are separated. So if we got a miss by 1 or whatever, we just go to poisoned memory again. So it looks good. Yeah, of course, the same approach if we just need to understand what is the original problematic memory, we just do reverse mapping on the memory in shadow. So it works fine. So the last remaining part is how to make it work with poisoning. So we need to understand when to mark the shadow memory. It's really easy. We need to intercept all functions from libc. New, malloc, free, delete. String functions, because string could allocate, for example, store string no. What's the function to allocate memory in strings with a copy of the string? OK, tell me later. So we need to resolve all the addresses when we allocate memory and mark all of them as addressable. So vice versa, when we free memory, we need to mark them as poisoned. Really simple. And if we go with stack, we need to do these steps only when we enter the stack, so enter the call function and exit it. So it's only done by compiler, but not the runtime. So what's the cost? We only need to switch compiler flags. The typical slowdown is twice. Overhead in memory, in heap memory, usually twice, thrice, and the same for stack, because we need to locate all the red zones in stack memory, right? And to make it better, optimizations are applied absolutely everywhere. So first of all, we compress memory. We also skip the checks. If we're trying to go through the array and access all the bytes one after another, we can just merge them because it's done by optimizer. And yeah, we can also skip a few of them based on different inputs. So how to make it even lighter? Because twice slower, it's not a good idea. Let's make it faster. First of all, we can skip instrumentation for code. If it's critical for performance, if it's a critical path, why not? And sometimes we have a function which we know it's fine, but Sanitizer probably flags it as a problematic. We can ignore it. And how do we do? This is by putting a small attribute. It's for Clang and also Sanitize. For GCC, you have approximately the same attribute, but the main idea is to just to annotate a specific function or memory address, a global variable with this declaration. And then we can skip, if we have a really large amount of code, we can leave code as is and specify all the ignore list via regex or just names in a specific file. Then in runtime, when we got our program up to run, we can disable checks in external code, for example, external library, OpenSSL, whatever, any existing codec, by just telling suppressions. It's an environment variable, so it means it doesn't affect instrumentation. It just ignores reports for a specific part of code. OK, another idea. We can tune down instrumentation without turning off entirely. It leads to linear code, and what we usually do. If you are not particularly interested about use after return, we just turn off this one. Use after scope, same. Then, In runtime, we can also, without any changes to code, disable specific stack overruns. Not so good, but if you flag it with false positives, we'll speak about it later, you can also use it. Then, sometimes the leak tracking could be disabled because it makes your program a bit slower at the end of execution. We can just go and tune it. And finally, if you're not satisfied about how fast are you failing, we can enable trap mode, and it's a different approach how we coach all the problems. It's not about Sanitizer library handling this, but us just reacting to a specific Unix signal. And finally, we can experiment with hardware. So it's a different kind of sanitizer, hardware sanitizer, and it's based on target memory support, which is currently it exists in ARM62, so it's probably about saving us from problems in your mobile devices and server programs. For Intel, it's quite slower to adopt because it's only in recent compilers and only in recent hardware. So I don't know if anybody have this error lake. I don't, so I cannot experiment with this. So the situation is good. It's really, really experimental, so give it a try. Then we got Leak Sanitizer. It's kind of a subproduct of Azure Sanitizer, and it's enabled for us for free because we already track all the mallocs and frees, right? So we can understand where does memory leak. Yeah, so it's really simple, just to subtract things. So it just reports all the leaks on program exit. It could be a bit slow. But if you're not interested about slowness on the program exit, you should be probably fine. And you can also enable it without Azure Sanitizer if you are tracking only leaks. What could be a problem with Leak Sanitizer? It's really opinionated because, first of all, it's not enabled by default, but it's fine, you can tweak it. But it requires a really specific program design. We actually allocate a lot of things in main. So are we interested about a leak? Is it a leak if we just allocate something in the beginning of program? No, it isn't, yeah? So sometimes you have a really specific pattern. So you have a handler of, I don't know, event-based system or HTTP messages, and then you need to understand, okay, do I leak something during a processing iteration or what, yeah? So for fine-grained checks, you can hack into LLVM internals. Probably for GCC there should be a really similar one, and just call it in your processing loop. So it means you will have it reported not at the end of program, but just in the middle. Be aware that checks are accumulated, so it starts from the beginning of the program, but it just not differential. It accumulates all over the loops. If you're not satisfied with this, you can go with gmalloc. It allows the same approach as with Leak Sanitizer, but it also allows you to just put two different calls and make a difference between two of these. The problem with gmalloc is it's dead. So first of all, it's not compatible with Azure Sanitizers. So you probably could replace it with tcmalloc, but please be aware if you're checking leaks, Sanitizers are probably not the best tool, not the best ergonomics you will have. What about platform support? Who likes Slang? Who likes GCC? Okay, so actually, the situation is support in Slang is a bit better. GCC is catching up for Sanitizers, I mean, yeah. So Azure Sanitizer is supported everywhere. Linux, macOS. Leak Sanitizer is a bit different. So it doesn't work with Apple because Apple has a really specific implementation of this, but if you're using Slang, it's all good. For Trace Sanitizer, it's really limited. It works only on 64 bits, but it's probably fine. Undefined behavior, lucky us, it's everywhere, so you don't need to pour const expressions everywhere. You can just run undefined behavior sanitizer. But you should use const expressions as well. And for Windows, no clues, sorry. So what about false positives? False positive is when you don't have a problem, but you are told you have. Okay, it's really, really rare with Azure Sanitizers. It could only happen when you mix instrumented and non-instrumented code. Yeah. For Trace Sanitizer, it's totally another situation. For Azure Sanitizer, it's probably fine. Typical example of this array situation is container overflow. You can check it later. in the code. So the reason is, if you have some functions in inline headers and you have some functions implemented in libc, you'll get different behavior because libc is not instrumented. Yeah. So usually you just slap this as an options and go away with this. Yeah, and compilers, they're trying to mitigate this by putting some annotations in libc. Probably Slang is okay. So it was about false positives. What's about false negatives? It could be done. It could be found, actually, yeah? Because if you have any unaligned access, you're in a bad situation. Please always align access. It's good for caches, for L1, it's good for performance. And it doesn't work if you are working with already hardened platform, like Debian or Gentoo installations. But it could be also not a big problem because you're working with your own build. And picking pi, it's not easy as a pi. It's a typical source of confusion. Usually people say, okay, if you are messing with PicPy, you'll be in a big problem with sanitizers. And partly it's correct. So if you see any of these symptoms during compile time or runtime, you're probably trying to mix PicPy or non-pic non-pi. So the idea is, pic is relocatable binary, and pi is relocatable executable. Executable should be relocated just to load it everywhere, anywhere in the space, in the memory space, just to avoid any hacking to this. So you just build all the code relocatable with all the offsets, and it's up to linker to resolve all the offsets and make a proper image of your program and all the libraries. So just use fpic, fpi, and you can easily identify if you are not using them. So the common problem with sanitizers is, okay, if you see this, it could be a helpful cheat set for you. Yeah? So sometimes PAM is limiting you. Sometimes you have SE Linux enabled. It doesn't work. Sometimes some kernel flags are not enabled or disabled, and you have another locator in place. ASLR could be disabled. It shouldn't work. You have non-pi, non-pic binary, and somewhere your dependency, binary dependency, is non-pic, and unfortunately it shows topper. And all the symbols are provided by runtime, reporting functions, interceptors, so you can probably see report store, report load is memory access, assign init, it's an initialization to replace all the things. So it's a pretty huge library. And as I have different implementations for LLVM, GCC, but it should be probably okay because compiler and linker, they know which implementation is it. And you cannot actually mix and match them. You need to build the same program with the same set of sanitizers. So how does it work for different platforms? So actually for SLN GCC, you can observe different behaviors. So sanitizer runtime could be static or shared. You can easily identify it by checking this, and you will see in a minute how does it work and what could it make a problem for you. Yeah? You can actually switch behavior by specifying some linker flags. It's totally fine. For different systems, it's only one approach to use only shared sanitizers, but yeah, please be aware of this. For macOS, it works significantly different. So, since I'm presenting from Bloomberg, and I'm allowed to say a few bits of our internals, so we use Linux, we use GCC, it's really good. We use CMake, and all these things are given to us by CMake toolchains. It's really good and ergonomic. We don't need to switch anything at all. And we use statically linked binaries with PIC, and with statically Basan, it allows us to have a really, really consistent way of enabling this. So all the things about sanitizers are injected from the build system, homegrown, of course. And we run unit tests under sanitizers. It helps us to find a lot of bugs. And if a team is willing to onboard the safety team, we can also run integration tests. I'll speak about it later. So what's about memory sanitizer? Don't confuse it with address sanitizer. It's totally another thing. It catches only one specific class of errors. Reads from uninitialized memory, and that's all. It's only error it catches. So you will see this error, this report from memory sanitizer, but yeah. Compared to address sanitizer, which catches a lot of illegal reads. So the problem with memory sanitizer, it's not compatible, it's extremely slow, and all the dependencies, they need to be rebuilt, even libc. So it's not a practical choice, so better use Asana. And with Thread Sanitizer, it's a different beast. It's really hard to make a C++ program behave correctly in a multi-threaded environment. Even harder to find bugs in this. And actually, it's a problem. Can we write a correct problem in C++, correct program with multiple threads? So this year, we got a really good talk in CPPNC about porting some primitives from another language, from Rust actually, to C++, from Swift also. It didn't succeed, unfortunately. So the lack of language library primitives, it makes it extremely hard to make programs. So don't try to imitate Rust. Try to find bugs. Unfortunately, it's only about heuristics, but these heuristics are so good in Thread Sanitizer. So it's only a glance on all the bugs we can catch with Thread Sanitizer, and it's quite a lot. So, for example, let's go with a really simple program. We got state, it's not atomic, so we got a problem. It's not obvious how to spot it if the program is larger than 3 lines, correct? So let's trace and observe what happens. First of all, Sanitizer, it doesn't stop your program. It continues execution, but it flags the problem for you. So it says, OK, from thread 1 in this specific lambda line, we see this access. And we can just go and check what could be a problem. So it's the first example. Another example could be a bit more complicated. So we have a flag which controls the execution. So based on value of this flag, we adjust where do we go, which branch of code we do execute. So it changes execution flow. And again, Thread Sanitizer allows us to observe this changed code flow. So it's a different heuristic, yeah? But it's quite helpful for us because it's really common. What's about the costs? It's bad. So actually, you don't run your program in a real environment with Thread Sanitizer. It's probably mostly about unit integration tests, and it's really heavy. And it strictly requires FPI. And yes, it's costly, but it's about heuristics. Unfortunately, it gives a lot of false positives. And yeah, by the way, all the calls from libc, std C++, and all this mutex-related stuff, it cannot be instrumented actually because we don't rebuild it. So it's all of them, they're intercepted. So you can see pget mutex logs, pget join, and things related to concurrent access to resources are intercepted. So we know how they work, and let's try to go for a few examples about interactions, static, shared libraries, false positives, and speak about cross-language support. So first of all, we have an application. It's not sanitized. It says blue. And we got the chain going to libc++. Unfortunately, static linking to libc++ is not supported at all. So it just doesn't work. So we need to use only shared. libc, for memory sanitizer, you also need to use instrumented libc++, but it's a really extreme case. So we use only shared library, right? So if you instrument both of app and library, it works perfectly for static library. It's a perfect case because all the locations from a library and from application are tracked. So we cannot miss a thing, right? No false positives, no false negatives, which is also a good thing. And we don't instrument libc++. Another scenario, we don't instrument application, but we instrument only static library. So what should be done here? First of all, it doesn't work without build changes because we need to link sanitizer library. So we don't instrument code, but we still need to specify fsanitize address as a linker flag because it links to the runtime. It's fine because we can control linking because we are building the application. Then, if we got a static library, we can easily got a false negative. So imagine the situation. We allocated some memory from the right side. It's a library, instrumented code. And we have a bad access only in the main application. So this goes unchecked because we cannot just check anything at all in application. It does not have instrumentation. So you will miss some of the problems. So it's not flagged. Then, if you go vice versa, we instrument only application but not a library. Works fine. Again, allocations from executable are tracked, from library not tracked. At least we don't have any false positives. And what about dynamic library? Because it's a really common case. So if you instrument both of them, it works perfectly the same. Of course, we need to link to the shared runtime because we need to have the same implementation for application and for dynamic library. So just a matter of switching the link of flags. And if you instrument only dynamic library, it's an interesting case because the main application is not aware at all about linking Asan runtime. So the library is rebuilt, it's fine. But then if you just want to run the application, will be exposed to this problem. So what should we do? We should only load a library. So actually what the sanitizer flag to linker does, it just instructs linker to load Asan runtime. So we can easily do it without any adjustments to the linker, only with LZ preload. So it puts the Asan library as the first library which should be loaded. So all these things related to libc functions exported from libc, they will be intercepted by this library. So yeah, it works. So what if goes a little more complicated with tree sanitizers? So let's try to instrument only application. Yeah, we're trying to build it. We have runtime, it's shared, as you remember, and we're trying to intercept, not us, but runtime tries to intercept all these things about locks, atomics, and the rest. So the bit behavior in the library is not checked. Actually, we expect this. And the good thing is we don't receive any false positives. Yeah, it's fine because we don't expect them to be caught. But luckily, we can see a specific class of problem caught even we don't build a dynamic library, a dependency as instrumented. So how does it work? So let's write a really simple program with spin logs. Oh, I could be fired after writing my spin log implementation with all these atomics. But yeah, it should probably work. So if we just have the spin log implementation in library and we have an application instrumented, we expect them to be flagged because acquire log and release log, these functions, are caught if the library and application is instrumented, because it's a heuristic. Thread sanitizer knows about all the primitives, and it can figure out how does it work, right? But if you replace it with the system mutex, we just call to pitchet mutex log, pitchet mutex unlog. So again, the shared library is not instrumented, but the application is instrumented. We got no problems at all because thread sanitizer, it intercepts all the calls. And it doesn't require the shared library to be instrumented to see this case, right? So we don't expect any false positives. Again, it's about no errors to be reported for a totally normal scenario. It's a normal scenario. I don't see any problems here, right? And this is because runtime intercepts all the functions. So it works well. So actually, if you go with this scenario, it could be a big chance of catching even the errors which are not related to your instrumented application. It will also catch a few problems in the dynamic library. And at least it doesn't say about false positives in the library. So far so good. What about cross-language projects? So if you're trying to integrate libraries in different languages, how does it actually work? Because it's a different language. So if somebody goes in and tell, OK, let's rewrite everything in Rust, we can probably go with this. But we also need to maintain guarantees about memory safety, because if you're just calling C++ library from Rust or vice versa, we could be easily exposed by bugs introduced by the boundary of the libraries, right? So first of all, how does it work for a really simple program? Of course, a Rust program can crash. So we write this code. So first of all, just small introduction. We introduce an array here of 4 elements. And then we got a pointer to the beginning of this function. Oh, sorry, to the beginning of this array. We move it to 10. So it's definitely out of bounds. And then we just go and try to dereference it with unsafe. So of course it fails because it's unsafe, right? But if you have code in your program which has unsafe, or you have any dependency in your dependency graph in Rust, which introduces unsafe, you could be facing this problem. So it's really crucial to introduce this for your program. So Sanitizers could even help for Rust because it's built on LLVM. So let's see also how does work in cross-language projects. So imagine we have a Rust application, we have a dynamic library, and all of them are instrumented. So we'll coach the problems between these boundaries. So first of all, it's not so simple because we need to introduce a special bridge for the sake of this example. If you don't use bind-gen, if you use CXX, it's a really popular way of introducing dependencies in C++ from Rust, you need to generate a small bridge, a small program. So all of these paths are built with sanitizers, and all of them, they're using the static runtime. So it's quite different from the topic we discussed before. So it's not shared runtime. It's only static runtime, but it works. First of all, imagine we have a library called libfoo. It's linked to static runtime, so we just rebuild it. And then we go to the CXX crate and make a bridge. So libfoo, it exports the header file. So we are building this bridge from a declaration, which is placed actually in for h. It could be just the whole content of the file. And then we write a small prototype in Rust. So it's all you need to write to make a binding from C++ to Rust. So it generates a static library, CXX bridge, and we need to instrument this as well because it contains the glue between systems, between Rust code and C++ code, right? So how do we do this? So first of all, how to call this function? In main, we introduce a variable on stack. Unfortunately, the syntax is not so good because we cannot just do it in normal Rust way. We need to call a special macro which introduces a variable on the stack. So the same, it says testing test, and we're trying to, as we did before, to dereference at the 100th element, right? So we built all the things with sanitizers. And what should we see? Hooray! We have a problem in C++ library, which is noted here. I didn't enable stack traces, so we don't have any good stack traces, sorry for this. And we try to read a byte of size 1, and this is invoked by the main application. So it all sits in shared memory, and we got normal, except for stack frame, but it's a problem with my example probably. We can observe it. So the problem is, it's not so stable. So it's only presented in nightly compiler. It's the way you introduce unstable changes. And the sanitizer feature is unstable so far. So probably should be stabilized soon, and then we can get a normal way to introduce changes, to introduce sanitizer to the normal build. So the build is tricky because, first of all, we need to not use just cargo, but use a special build script, which is actually the part of cargo, trying to build this CXX bridge. So we specify, okay, try to generate the source in main.rc and specify this specific flag. So it's a change required for program for the bridge to be instrumented. So we instrumented this. We instrumented the whole program by specifying Rust flags. Because it's unstable, we cannot just pass it. We specify -z, which means unstable. So after this, we got the whole program in place. So unfortunately, it works only in a specific case, only with static runtimes, and only if you specify. If you don't specify sanitize address, as we did with our C++ program, the main file, we cannot do this. We need to say explicitly about please link this runtime. And this runtime will be LLVM runtime, not Rust runtime. It's a mess between different runtime implementations in Rust, LLVM, and GCC. But if you don't go with this approach, you will see this error on start. So incompatibilities between different runtimes, it's a huge issue, and we really hope it will be figured out soon. So summary, it's built upon LLVM, it works perfectly, so the implementation is almost the same, but the binary is different, and we can use the same sanitizers, heap, stack, leaks. I don't know, do we need to have 3 sanitizers for Rust, but who knows. And yeah, it works fine. Finally, we got how to use them, we got how to build the code, and we convinced to use them actually. But how and where? So first of all, it's absolutely mandatory that you need to run all the unit tests with sanitizers. If you don't, please do, because it allows us to catch bugs really, really early. And it's good only if the code coverage for your program is good. Because if you don't cover any code path, specific code path, the error couldn't be seen. But what is usually forgotten is data coverage. It's not code coverage, it's data coverage. It's really rare to introduce the changes to code coverage. Sorry, data coverage. And if you have a program which is considering different kind of inputs, like JSONs or files, image files in a codec, which is a really, really common situation with all the CVEs, it could be a problem. So first of all, for code coverage, we got the same coverage for 78%. Okay, we miss 2 parts of code, so it doesn't matter. If we are sure that the main parts are covered, it's probably fine. But if you go and check the data coverage, we actually have a really, really big problem with 2 of these squares, because it could contain a really, really malicious input, and it won't be caught by your code, because the code coverage could be 100%. But if you don't catch this specific datum, you'll be out of luck. So for this, first of all, we run unit tests. Then we should probably approach more running for integration tests. So more code paths exposed to adjacent sanitizers. If you run integration tests, it's usually like almost end-to-end. You are much closer to real scenarios. And of course, you need to measure coverage not only for unit tests, but also for integration tests, because it tells you so much about what do you miss. For unit tests, it's probably okay to have 80%. But if you miss something for integration test, it could be a really big problem because you're not checking this behavior. So how to deal with missing data pieces which are not covered for data coverage? So the most working solution probably is to use fuzzer. It's not for every application. It's not for every scenario, but the main idea is you provide an entry point for external program for libfuzzer, and fuzzer calls your program with mutating inputs. So in this case, you'll be provided with covering all this, probably all of this, data mutations. So you can spot really, really rare code paths triggered by specific memory data, right? So it's a black box testing. If you're writing property-based tests, like quick check in Haskell or hypothesis in Python, you could probably write them. You'll probably see better coverage because it's white box, you know your program. And the good scenario for fuzzing is when a program is really really well structured. So it's either a library, or is it a database, or should it be a codec for images or sound, which is a main part of modern attacks? It's good, yeah, because you can easily write a function like this on the right side, and you'll be covered. The best scenario is, for example, HTTP server, a system, event-based system. You cannot just find a way where you can introduce this function because it's just a caller. So it could be quite difficult. And for example, yeah, for data-driven applications, it's really, really strange. So a good idea comes to mind. Okay, what if you run in production? No, it's not safe. So actually, all of sanitizers are marketed as non-production ready, and I can understand people. They don't want to have any guarantees for application, but sometimes it's probably fine. Because, for example, undefined sanitizer, it doesn't break any behavior. Trace sanitizer, I could not recommend this. So the problem with them brought to the production system could be mitigated by providing a really, really minimal runtime. So the changes from additional behavior to a program shall be minimal. And yeah, if you think about safety, the undefined sanitizer is most safe. Other sanitizer is probably good, and please don't use thread through memory for runtime for production. What to consider about running them in kind of production system is how to recover. So for Agile Sanitizer, unfortunately, it stops on the first error. It makes sense, as we had in the first talk. In the first keynote, you cannot just understand what's going wrong. So sometimes you can just want to continue. So set this flags, you could be okay. For undefined, it's fine. It just continues execution, so you don't need to introduce any flag changes. For tree sanitizers, by default, it just reports. Great. We just observe logs and it's fine. For leak sanitizer, as we spoke before, we can track periodical reports, but usually just reports on exit. So where to place it if you want to write as a part of production system? Don't tell Bloomberg at all this. So it could be a canary deployment or a blue-green deployment when it's totally good to push some traffic to a test instance. And then it could be an idea about mirroring traffic. So imagine you have all your systems, including dependencies, really, really isolated. It could be a mock deployment or a mock service or mock data source. And you just route some traffic from input system, from HTTP, for example, or multiplexer for event-based system, and you observe the behavior. So it's exactly the same data you run a production system on, but you can, if you can isolate this into a really, really isolated environment, you can easily spot problems on your prod. So good idea. Why don't try it? So to wrap up, Sanitizers are really, really powerful tools. So they're available for all the major compilers and platforms, and it's a result of work for 10, 20 years probably. Okay, not 20, 15 years. And there are plenty of open source implementations. All of them are open source. And they can also work on component boundaries between application, static library, dynamic library, and even between different languages. Unfortunately, sometimes it's really difficult to integrate it with a build system, but if you're using a really, really modern C++ or some kind of in-house build system, it could be fully abstracted from you. And yeah, if you want to run it, please try to run it on code and behavior as much closer to the real system as possible. So thank you for listening. Thank you for having me. I'm ready to answer your questions.
Yeah, thank you for the talk. You had lots of good info here that I don't think is in the documentation. So do you have any recommendation for other sources for all this?
Yeah, absolutely. The first thing on Google, you'll find when you type Agile Sanitizer. So if you type Sanitizer, you'll probably be provided with some kind of COVID-related stuff. But for Agile Sanitizers, you'll be routed to an obscure, old, and deprecated. So by the way, the slides link is here if you want to check, but it will be available probably for all of the speakers. So it's really old. It's 10 years old. So usually you just go to Selang documentation, into Selang LLVM or GCC documentation, because it's hugely different. The wiki on Google GitHub Sanitizers is really old. And for me, it's main source of documentation, and it's usually up to date. And you can also check which functions and which behaviors are introduced in a specific version, because you could be easily sitting on GCC 13, for example. Yeah. So please check only this and don't trust Google. Don't trust LLMs about this. Go to official documentation, check this. And for us, there is a unstable book, Cryptonomicon. Oh no, yes, Rastonomicon. It explores a lot of things about this. So official documentation is the way to go.
You had a page for address sanitizer where it's some problems for different systems.
Mm-hmm.
I think it's on, is it?
Let me try to find it. So it's about integration between libraries or false
The
positives?
systems and different states, like I think the memory mapping as an example.
So this is the first page of memory.
Linux.
I got you.
Can you say a bit more about the problems that you have? Is it like silent degradation, or do you get some warnings?
So you mean, are you provided with any information about when it does not spot a problem, when it provides a false negative?
This was the page where you had these extra like SE Linux, and if you remove memory max,
Ah,
and you have these
yeah.
problems.
Yeah, I got it. So usually, you will see a problem. Then
Was that for address sanitizer, I think?
yeah, but it's probably a bit later. So false positives. Yes, this. So this here.
Yes.
So yeah, usually your program won't just run. So you will be presented with unable to load, unable to map shadow memory, and all the stuff. So it's really, really explicit. So all of these items on this slide, you'll know about this because you cannot just launch your program. So it's not silent. A silent problem could be only if you are missing instrumentation of some of your dependencies. It's the only way. All these problems are preventing you from run your application on a specific system.
Thank you.
You focus mostly on Linux, so do you have any hints for people dealing with Microsoft Visual and Windows other than switch to Linux?
Yeah. Switch to Linux. Another good advice. Unfortunately, I'm only aware about a Slang implementation ported to Windows, and it's a quite good state of this. And it means it provides all the instrumentation for free, because instrumentation is done not in a compiler, but in the backend of LLVM. So it means if you have LLVM implementation, you'll get it for free, as Rust did it, as Swift did it, so all of the things. The only problematic part is runtime, because on Linux I have a really, really specific way how to intercept things. So I can probably say that if you go with a Slang implementation on Windows, you'll be probably in a better situation. But I definitely heard when I'm reading blog rolls about MSVC, I definitely see a lot of mentions of sanitizers. So it means it exists. Probably it's in a good state, but I cannot tell you does thread sanitizer, for example, exist. Undefined behavior sanitizer, it definitely exists. Address sanitizer, it could probably be in a good state, but for the rest, it could be a bit more complicated. So sorry for lacking for Windows.
Yeah, through my experience, I mean, the address sanitizers works quite well, but the rest, I mean, the thread ones and everything, yeah, basically.
Yeah. There are extra sanitizers. They are not actually so stable, and they use it only for niche cases. So it could be explainable why they are in experimental state.
Yeah, okay. I have a question. So after setting up these sanitizers, are we 100% sure that we will not have any memory errors in production? And if we find such errors during production, what are some steps to do? Any ideas?
I was sure about the program. So first of all, you don't have any false negatives. So if sanitizer tells you, okay, there is a problem, it most probably a problem. Otherwise, you can just slap a notation on this. So if you find it, you're provided with really, really good explanation about what went wrong, especially for address sanitizers. The stack trace at the end, it shows you exactly where do you crash, why do you crash, what's the memory address, and you also present it with a shadow memory snapshot. So it provides a lot of information, so you just get exactly the same source code, the binary. You don't need to have a memory dump, because it's almost self-contained. So yeah, I can just suggest to look after these things onto these slides, and it's pretty much explainable. For trace sanitizers, you presented about data race condition. It's more complicated. At least you are given information about which threads are racing and on what kind of heuristics are the reason of this report. So you can probably derive some information about this. So are we racing for access to one specific variable, or is it a deadlock? So it could give you some information. But the rest is for developer, of course.
Okay, time is over. Thank you.
Thank you. Thanks so much again.